Hey guys, welcome to this session by Intellipaat. Statistical analysis is so much important for businesses across the globe, and I'm sure you guys already know this. But did you know that Microsoft Excel is a very advanced tool that all of these specialists use? Well, keeping that in mind, we here at Intellipaat have come up with this session to address all of your questions with that. Well, before we begin with this session, make sure to hit that subscribe button and that bell icon so that you never miss any updates from us. And now, coming to the agenda of this session, we start out by taking an understanding about what linear regression is and how it works. After which, we'll check out everything there is to know about ordinary perfect squares, and we'll have a hands on implementation of how to work with statistics with Microsoft Excel. And lastly, we'll be checking out how we can perform statistical analytics in depth with Microsoft Excel and a lot more in this session. Well, guys, without further ado, let's begin the class.
First things first, the concept of linear regression, of course, stems from simple concept of trying to predict numeric outcome given a set of dependent variables. So there are two important things. The first one is you have dependent variables and you also have independent variables, right? You have dependent and independent variables. Independent variables are the ones which typically are the target variables that we use to predict. Like for example, if I'm interested in predicting sales as a function of, let's say, money spent on ads, then sales is typically my target variable. So sales is basically in this example dependent on ads, hence sales becomes my in this case sales becomes my dependent variable and ads becomes my independent variables, so to say. So the thing of course is that when we talk about dependent and independent variables, there are of course you can take a couple of other examples as well. Let's take the example of I'm interested in predicting the stock price of a particular company as a function of let's say the sentiment of, or let's say the number of positive articles, sentiment, let's say the sentiment, the public sentiment, and let's say there could be numerous other reasons why the stock price could vary. So this becomes my dependent variable. Stock price becomes my dependent variable, and everything else, all the other variables, will become my independent variables. So in this particular case, as you could clearly understand, a dependent variable is basically that variable which is responsible, or which is the variable that we're interested in, or the or that particular feature that you're interested in trying to predict. It's also often referred to as a target variable. A common term is also a target variable. You will also come across terminologies like that. So do not get worried if you see terminologies like those. Okay, cool. Now, next thing is, let's take this particular simple example. Now, when we talk about linear regression, again, as I said, if you take a simple example like let's say we're trying to predict the yield of a crop based on the amount of rainfall that we have seen in that particular year. I'm trying to predict the yield of a crop based on the amount of rainfall. So if I want to solve this particular problem, what do you do? So what I'm saying is, historically, there is a relationship with the amount of rainfall, that there is a relationship between the amount of yield that we have seen for paddy, or let's say wheat, and one of the primary drivers for that particular thing is, let's say, rainfall. Mind you, rainfall may not be the only variable that is causing this. There could be 100 other reasons why in a certain year, certain crop has yielded a certain value. But one of the more popular, or one of the most one of the primary reasons, of course, is the amount of rainfall. So let's solve it with a single variable, and I am hypothesizing that, or in with my limited understanding about how agriculture works, I am hypothesizing that yield can be predicted. I'm saying yield can be predicted as a function of the amount of rainfall that we see. This is not a bad hypothesis, to be honest. This is a simple function, to say the least. But of course, I need to validate this particular hypothesis. What I would have to do is I'll collect historical data, right? So let's say I'll collect historical data from various markets, from various regions. So I'll have yield, and alongside yield, I let's say also collect the amount of rainfall. So from different regions for the same amount of land, right? Because I shouldn't be comparing the yield of 1 acre land versus yield across 100 acres land. That would be an unfair estimate, right? So I'm assuming that the yield that I'm talking over here is, let's say, per acre. So is number of kilos per acre or number of tons per acre, let's say, something like that. Okay, in a given year of 365 days. So I capture all the data points. Let's say I have 10 tons and the rainfall is, let's say, 250 centimeters in the complete year. Second is, let's say, 20 tons, 250 centimeters. Third is, let's say, 23 tons, 180 centimeters, and so on and so forth. Let's say I collect all of this data historically, and let's say I collect maybe 100 observations from different parts of the country. Now that I've collected all of this data, the next step is, of course, to go ahead and try and find if there is a way to extract a relationship between my yield and rainfall, right? So what would you do? Sorry, what would you do? So you would simply go ahead and we'll try to, if you were to visually understand this, you can draw a simple scatter plot, uh, rainfall on the x-axis, on the x-axis, and then you can have yield on the y-axis, and then you go ahead and you create all these points. Whatever points that you have over here, you simply go ahead and create all these points, right? So different points that you think are possible. Now, given all of these points, the idea is you would want to identify this relationship, this particular function that you're seeing. What is this function? Linear regression says that this particular function that we have is a linear function, right? What I'm saying is that yield can be predicted as a linear combination of your rainfall, some linear function of your rainfall. So when you say a linear function, what do you mean? It is basically that I can somehow come up with a hypothesis which says, something like this, which says that yield is equal to, m times your rainfall plus c, something in this linear equation format. So for arbitrary values of m and c, when I say arbitrary values, for different values of a and m and c, this whole equation from our knowledge from in mathematics basically says that it is a simple straight line equation, something like that. It could be different straight lines for different values of m and c. It could be different straight lines. It could be a line like that or line like this. So different values of m and c will yield different straight lines. I am trying to identify that one single line, right? That one single line that cuts through as many data points as possible, or that is as close as possible to as many data points, right? I can create different values of m, and I can create different lines, but there is one specific value of m and c which is as close as possible to all the data points, right? But when I say close to all the data points, how do I measure close? How do I measure this proximity? So one of the most popular measures over here is that you would want to make sure that every point is as close as possible to the line. That is one way of looking at it. Or another way of saying the same thing is, for every value of x, there is a actual value of y. For every value of rainfall, there is an actual value of rainfall, and there is a predicted value of rainfall, right? This is the predicted value, this is the actual value. This is basically an error. That delta that you see over there is nothing but an error. So for example, if you take this point, or if you take this point, this is the predicted value, while somewhere here is the actual value. Somewhere in this particular range is your actual value. So that difference is the error for that particular data point. Ideally, what I want to ensure is that the difference between the distance from the line to every other data point should be as small as possible, or I want to make sure that this error prediction is as low as possible. Whatever value I predict, I want to make sure that the error is very, very small. Now the question is, this is great. The fact that I want the lowest possible error is great, but how do I make sure something like that happens? Okay, so to do that, it's actually pretty simple. There's nothing very complex here, and let me try to bring this up. It's quite simple to ensure that the actual values and the predicted values are not far away. So here's how it goes. Let's say this is how your data. This is your data. All that I'm saying is this is nothing but your predicted value. So this is your yield. This is your actual value. And then when you create that particular line, right? These are all your data points. That is a line. So and line basically will have an equation. So yield is equal to 10 plus 5 times rainfall. Let's say you have a line like this, 10 plus 5 times rainfall. That's the or let's say whatever, 10 plus 0.5 times rainfall or 0.1 times rainfall, whatever is the value. So there is a predicted value. This is the predicted value. What I want to make sure is that for every given value of rainfall, I substitute this value over here. So let me actually take a better equation instead of this. This equation could give me results which are haywire. Let's do it this way. Right? 0.5 plus 0.1 times rainfall. Let's say this is one particular equation. Right? I want to make sure that the predicted values for every data point that you see over here. Yeah, Arnab, we'll get to that. Good question. How do we get to the best fitting line? We'll get to that. We haven't done that. Let's assume for a minute that we know what it is, and we will solve equations right now in today's class to identify what those values are. But we'll get to that. Let's assume for a minute that we know what they are. Okay. So what we're saying is you predict if the rainfall was 250, what would be the predicted value? Can anyone guess? So if the rainfall was 250, so it'll be 0.5 plus 0.1 times 250. So this will be 25.5. So the actual value is 10, but the predicted value will be 25.5. Similarly, in this particular case, if the rainfall was 180, the predicted value of yield would have become 0.5 plus 0.1 times 180, so which would have become 18.5. So this value would have become 18.5. Right? So you have the actual value, you have the predicted value. Now we can always compute the difference between the actual value and the predicted value. This is the actual value and this is the predicted value. You can always compute the difference between the actual value and the predicted value. I want to make sure that I come up with that particular line where the summation of actual values minus the predicted value square for every term from I is equal to 1 to n. So for every value, the actual value and the predicted value. So whenever you see this means it's the predicted value. It's called y hat or y cap, right? So I want to make sure that this particular value, and I can take the mean. So this is referred to as mean squared error. Yi minus yi hat is nothing but error, square of the error, and the mean of that particular error if you observe over here. So what we are saying is, I want to make sure that this particular metric that we see over here, currently is minimum. Okay. I want to make sure that this particular metric is minimum. So just to let you all know, this metric is simply nothing but a measure of, if I were to put it, is simply a measure of how far away is this line from the data points. How far away is this line from the data point? The line is extremely far away, then what you will see is that the equation will have a very, very high value. If the line is very close, then you will see that this value will be a very, very small value. Okay, and first let's try and understand this. This is the most important part of the complete class. I mean, if you understand this particular equation, then we are all set to go ahead and actually solve this particular equation. So to give you a small intuition of what this actually means, just to kind of give you a feeler for what does this really mean, I have we're actually going to do a small Excel exercise just to kind of get a feel for it. So let's do a small exercise on it. Let's take a few values. Let's say this is yield, this is rainfall, and let's say 10, 20, 15, 30, 22. Let's take 5 data points for the moment. And yield is, let's say, 100, I don't know, 150. I've just taken the numbers a little differently for the moment, but 150. And then let's say we have 300, and let's say 250. Let's say these are the values that I have currently. Okay. And let's quickly insert a simple scatter plot. This is how the data points look like. As simple as that. Okay. 5 data points. Currently, this is how the thing looks like. Now, let me just add the axis titles. This is your rainfall, and this is your yield. Remember, this is my dependent variable, also called as the target variable. So don't get confused. It's called independent variable, or also called as predictor variables. So they are all the same names for the same thing. So don't get confused. If you read content from different places, different names are going to be used. So do not get worried about it. Wonderful. Okay. So yield versus rainfall, or actually it's the other way around. Rainfall versus, my bad. Yield versus rainfall. Cool. So now, if you logically look at these, this thing, I can have multiple data points. I can come up with different lines, so to say, right? One line, basically, if you look at it, let's try to do it here. You could come up with different lines. So one of the lines could be something like this. Another line could be, I don't know. Another line could be something like this, and then maybe one more line which goes, let's say, like this. Let's go completely bonkers on this, completely the other way around. So the point is, there are three different lines. For simplicity's sake, let's actually take two, just so that working with it becomes relatively easier. Let's take two simple lines. Red line, which goes like that, and then we'll take a green line, which goes the other way around. Sorry, let's go that way. Yeah, I have the red line and I have the green line. So quickly speaking, out of these two lines, each of these lines has a different slope and a different intercept value. Okay, has a different slope, because if you look at the red line, if you, for example, take this particular line, the red line, this has a positive slope, right? Almost a slope of 0.5, almost a slope of 1, because if you observe, this is almost at 45 degrees to x-axis, almost at 45 degrees to x-axis. And logically speaking, slope is simply nothing but the tan of this particular angle. So if you go back to your trigonometry, the tan of this particular angle is nothing but your slope. So let's not worry too much about it. Essentially, this has a positive slope, and what we're saying is this fellow has a negative slope. Okay, that's number one. Number two, the second point is, if you look at this particular line, this has almost it's almost close to zero, but that's okay. It has a negative. This has a negative intercept. Intercept is simply nothing but the point at which the line cuts the y-axis. The point at which this particular equation cuts the y-axis. Here, the intercept is almost around 250. This is nothing but your intercept. This has a positive intercept, right? From your understanding of what you've understood till now, out of these two lines, which will have a lower MSE? Will the green line have the lower MSE or the red line have the lower MSE? The red line should have the lower MSE. Fair enough. So from my understanding over here, I am actually coming up with two equations. I don't know if these equations are going to be correct. I'm assuming that they are the best equations. So for the red line, let's go with the red line first. So the red line equation could look something like this, where I'm saying that yield is equal to negative intercept. So minus 20, I'm assuming minus 20 plus 1.1 times, plus 1.1 times, let's say, rainfall. Something like this. I don't know. I don't know if this is even correct. I'm just taking a random guess at it, right? On the other hand, the green line could have something like this. Sorry, let me just, okay, it's too light. Yeah. Yield is equal to, so the green line could have an equation that looks like this. So it could have 250 plus, it'll have a negative slope, if mind you. So it could have a negative 1.2 slope or something, negative 45 degrees. If you look at it, it's sloping downwards times your rainfall. So two equations. I'm hypothesizing that these could be the two possible equations. And I am saying that this, out of these two, the red one should have the lower MSE. And let's actually go ahead and simply prove it. So the way you do that is, let's say, first things first, this is the red line and red line prediction, and this is the green line prediction. Before I have the red line prediction and the green line prediction, let me simply make a note of the red line equation. So where I'm saying yield is equal to, predicted value of yield is equal to minus 10 or something, what is that, minus 20 plus 1.5 times rainfall, minus 20 plus 1.1 times your rainfall. Similarly, for your green line, I'm saying this is 250 minus 1.2 times rainfall. Just a random guess. Arnab has a question. Yield can be 0 at the max. Hang on, just a second. Yield intercept equal to minus 10. Yeah, so a good point. Yeah, so at when the rainfall is 0, you're saying essentially the yield is negative. It's a good point, but then let's not get into that right now. I mean, you're right. Your intuition is absolutely correct. You typically, so in such cases, what we generally do is we fit the intercept to 0. We make sure that the line cuts through cuts through x-axis. Sorry, it cuts through the origin. So we force fit the line to go through 0. There are ways to do it. Basically we make the intercept 0 in such cases, but then let's not worry too much about it right now. I'm just trying to prove certain things, but you're absolutely right. Okay, cool. So for the red line, if you actually go by the prediction, so this is going to be minus 20 plus 1.1. So let me just do this, plus 1.1 multiplied by my rainfall. What is rainfall? Rainfall is this. Let's actually make this to make it a little, actually the slope would be a little larger. Okay, let's not worry about it too much. Just give me a second. And on the green line prediction, this is going to be 250 minus 1.2 times your rainfall, which is this 238. That's the prediction of your green line. So you have your red line prediction and you have a green line prediction right at this particular point. And yeah, currently I think I made a small mistake with this particular equation here because the red line needs to have a higher intercept cut through these data points. Let's just do a small change here. Let's make this 0. Let's make this 200, or let's make a small change. Instead of making it negative 200, let's make this 120. Just for, I've kind of hypothesized it incorrectly. Plus, let's do it this way. Sorry for the adjustments here. Yep. So these are my red line predictions and my green line predictions. Now what you could do is you typically compute the error now, and then you identify, so you compute your mean squared error of your red line, and you compute your mean squared error of your green line. And the way you do it is, this is your actual value. So let's come here. So to compute your MSE, what you're going to do is, it's going to be your average of actual value minus your predicted value squared. Essentially going to be the average of actual value and your predicted value whole squared. That is what your MSE is going to be all about, squared error. So this is my actual value minus predicted value, and then I'm simply going to do a square here. Yeah, average of variance, absolutely. So it's called sum of squared error. If you remember the ANOVA class, we call it as sum of squared errors. It's the same thing, yeah. It's basically variance only that you're doing over here. Correct. It's not star 2, it has to be to the power of 2 square. Similarly, you do the same thing here as well. This time it's going to be, instead of E5, it's going to be 5. Yeah. So in here now, what we're simply going to do is we're going to try and compute the mean squared error. So to do it, it's going to be average of these values, and similarly the average on, actually the looks like the green line has a lower MSE because the red line equation is slightly incorrect here. Let's do a small change. Let's make it 150. Let's make it 180. Let's go change a little. Yeah, done. So a small change. So now if you observe, the red line seems to have a slightly different, equation with almost a mean square error of around 40. So out of these two, what we are saying is that this particular equation has a lower MSE than the green one. But then the the whole point is that if I keep trying like this, there are infinite possibilities of M and C. There are infinite possible values of this 180 and the 1.5 or 250 or 1.2. I mean, logically speaking, because these are continuous values, there are effectively infinite possible values of this that I can get to. So where is the end? I mean, how do I find the best possible values of these two? There are infinite values of this and there are infinite possible values of this. And if I keep doing this continuously, there is no end to it. I might always find a particular value which is better than, let's say, the red line. As a matter of fact, I don't even know if there is a better value of M and C that would give me a lower mean squared error, right? And I would always ideally want a value that gives me a lower mean squared error. To actually show you how these lines look, I can actually plot those lines. It's not going to be very difficult. What we can do is we could try to plot all of these three together. Insert to. I can change the chart type. And just remove this from here. Okay. So for different values, and let me just change the chart type here. Just a second. So between these two currently, it's a bad equation anyways. It's not giving us a straight line equation. Of course, it doesn't give you a straight line equation. But technically what we are saying is that we're trying to draw a line. That's okay. Technically what we are essentially saying here is that each of these equations, this equation and this equation, out of these two equations, your red line seems to be, if you go back to this particular chart, your red line seems to be closer because your MSE is the lowest. And you please repeat the step where you got that graph. That's okay. I think that graph is probably not even a good representation. We'll come to that later. I think the crucial part is for you to just understand this chart, right? If you look at this particular chart, what I'm saying is that the red line, in this particular chart, the red line is closer to all your data points than your green line. Your green line is probably a bad fit. Red line is a better fit. That's the whole. That's the whole story in this particular chart, so to say. But then the question is, how do I make sure that I find the best possible line anyways? I mean, I don't even know if this particular equation is the best equation, or if I can find 100 other equations that will give me that'll give me my best. I can find 100 other combinations that will give me better values than this. So to do that, we're going to employ a simple concept, a simple optimization concept. We're not going to do it by optimization, but we'll use simple differential calculus concept. It's called, we'll apply something called as minima and maxima to solve this particular problem. So let's go back here. Let's go back to this particular step, and let's actually take another problem, and we'll try to solve that particular problem with different equations. And I think we will get we should be able to get an easy hang of how to solve this particular problem. Let's take a simple set of data. Let's say this is X and this is Y, and we have 5, 8, 7, 3, sorry, 7, 14, 6, 12, sorry, 6, 10, and 3, 7. Let's say these are 4 data points, right? These are 4 simple data points, and I want to find a linear regression equation wherein I can predict basically this whole data point. Data point would look something like this. This is Y and this is X, and these are my 4 data points, let's assume, right? Sorry guys, these are my 4 data points, and I want to find that one single equation that cuts through all these 4 points, and I want to find the equation of this. Yeah. I know one thing for a fact, that this looks like the form of y is equal to mx plus c form. I don't know what is m, I don't know what is c. I need to find the best possible value of m and c. But one thing that I know is, that come what may, I want to make sure that the predicted value and the actual value, I want to make sure that for all the data points, I want to make sure that this whole thing, this whole equation is minimum, right? For any data point, I want to make sure that this whole equation is a minimum. I want to minimize my mean squared error. So how do I do it? So let's assume that my equation is y is equal to mx plus c, right? Or rather, your predicted value of y is equal to mx plus c. You don't know what this is, but then let's assume that this is your y equal to mx plus c. So for every data point over here, you can simply compute y hat. For every data point over here, you can simply compute y hat. So if you just draw this line over here, your predicted value is simply nothing but, in this particular case, m into 5 plus c. Similarly over here, m into 7 plus c. Similarly over here, this will be m into 6 plus c and m into 3 plus c. For this thing, it will be m into 3 plus c. All of us okay with this? Because I'm simply substituting mx plus c, right? M into 5 plus c, m into 7 plus c, m into 6 plus c, m into 3 plus c. Okay, so this is my actual value and this is my predicted value. I don't know what MNC is. We'll solve for MNC in a minute. So my mean squared error equation will simply look like this. For data point 1, my actual value is 8 minus my predicted value is 5n plus c, the whole square, plus for the second data point, this is going to be 7 minus 7m c, the whole square. Similarly, for the third data point, it's going to be 6 minus, sorry, 10. Oh, sorry guys, sorry, my bad. Just a small mistake. This is going to be 14 and this is going to be 12, the whole square. And last but not the least, for my fourth data point, it is going to be, sorry, this is 10, right? It's 10. 7 minus 3m plus c, the whole square. 7 minus 3m plus c. Yeah, Jayant, Jaitirth, I've corrected it already. Hope this is 10. Yeah, you're right. All of us okay with this? Yeah. So now if you actually expand this complete equation out, you can, if you actually expand this complete equation out, simply speaking, what you're going to get is you're going to get a polynomial equation with MNC. Can you think of it? You'll get a second degree polynomial equation with MNC. So let's actually solve for it. Okay, this is I know half of you are like, hey, this is taking me back to my 11th standard or my 10th standard, but yes, that's the whole point. So if you actually expand this out, if you expand this equation out, 8 minus 5m plus c, if you expand this whole equation out, this is going to be, anyone? It's going to be 64 plus 5m plus c the whole square minus 8 to 16, 16 times 5m plus c. So a square plus b square minus 2ab. This is a square plus b square minus 2ab. Similarly, the second equation that you're going to get is 14 square. Anybody? What is 14 square? 100 and, okay, super. 196 plus 7m plus c the whole square minus 14 into 2 is 28 times 7m plus c. Similarly, for the third data point, 10 square is 100 plus 6m plus c the whole square minus 20 times 6m plus c. Last but not the least, 49 plus, what is this? 49 plus 3m plus c the whole square minus 14 times 3m plus c. Sorry, you're not going to get the square, just the 3m plus c over there. Sorry about that. Okay, so now I'm going to give you all 5 minutes and try to expand this out. Right? Try to expand this out. What will be the sum be? Totally super. 409. That's correct. So this is simply going to be 409 plus. Now let's come to this expansion in a minute. So okay, let's expand this out. So 5m square is 25m square. So if you actually sum up all the m square terms over here from all of this, so this is going to be 25m square, 49m square, 36m square, and 9m square. 563, Preetham, what is 563? Yeah, okay. So 25 plus 49 plus 36 plus 9. It's going to be anyone. Okay, please ignore. Okay, cool, very nice. 119m square plus, if you look at c square, 1, 2, 3, 4, this is going to be 4c square straight away. And if you look at MC terms, if you look at the MC terms, anybody, how many, what will be the MC terms over here? 5 2 is 10, 10 MC, 14 MC is 24 MC, 24 MC plus 12 MC is 36 MC, 36 MC plus 6 MC, 42 MC, spot on, perfect. So 42 MC, and you're going to get the M terms and the C terms quickly. How many M? Minus some M and some C. What will be that sum M? This is 80M. This is 96, 196, 80, 120, 42. Anyone? What about the M? N, M, and C both. 3M? Are you sure? It's 3M. It's all negative, right? So the whole thing. Okay. So this is going to be 438M, and the C term is what we're left with. And the C term is simply going to be negative 16, negative 28, 28, 20 is 48, 48, 14 is, so 14, 14 and 16 is 30. So 48 plus 30, 78. And that's it. So that's the complete equation. If you look at this, so logically speaking, what we are saying is we'll just rewrite this equation a little better. So if we were to rewrite this equation, what we're saying is this is 119m square plus 4c square plus 42mc minus 428m minus 78c plus 409 is your final equation. So your MSE equation is basically this whole thing. Cool, wonderful. So far so good. So we've all got equation, but now what to do with this equation? So what does this equation give me? This equation is basically, if you actually think of this, this is a second degree polynomial in M and C. So if you forget about the, if you forget about these terms for a minute, this basically looks like ax square plus by square. Sorry, if you actually rearrange this whole thing, a second degree polynomial, or if you simply forget the C term, just forget wherever there is C. This looks like ax square plus bx plus c. If you observe, if you forget wherever c, or am square plus bm plus c, if you just forget the c term for a minute, what does this look like? Am square plus bm plus c. Anybody? If you simply forget the c term, just forget about c for a minute. If you just take the m terms wherever there is m, this one, and forget about this as well. Just take this and the final constant, 19m 119m square minus 428m plus 409. Absolutely, yes. This looks like a parabola. Just perfectly right. So this whole thing, it looks like a parabola, and it is actually a parabola. But this is a parabola in more than 2 dimensions. It is a quadratic equation. Spot on, correct. Parabola, basically a quadratic equation. If you were to just look at it in M or in C alone, if you just looked at it from an M or a C, it would look like this. If you forgot about M, you can think of this as M and this is your MSE. So this whole thing would look like a parabola, or it could also be like this. If you imagine this was C and this is your mean squared error on your y-axis, this would look like a parabola, something like that. Okay. So basically what we're saying is that your mean squared error, your model has a particular value of M where your mean squared error is the minimum. Similarly, your model has a particular value, or your linear regression has a particular value of C where your mean squared error is the lowest. I mean, it cannot be zero, because if it has to zero, that means your line has to cut through every data point. So it's more or less impossible to have something like that. But what we're saying is there is a particular value of M. There is a particular value of M for which your MSE is minimum. If you see, this is a minimum most point. Similarly, over here also there's a minimum most point, particular value of C where your MSE is sort of minimum, so to say. Now what we are going to do is we are going to try and find these values of M and C. What is the value of M? What is this value of C? We're going to try and find what these values of M and C really are. But then now that this particular equation doesn't really look in a, because we're not looking at it only in a C or only in a M. So how does this actually look like? What does this equation actually look like? How it looks like? It looks like this. But then let me give it a try. Right? So it looks like this. This is M, this is C, and this is your MSE. So think of this, I can only of course draw in 2 dimensions, but think of this as a bowl. think of this as a bowl in your hemisphere. Yeah, correct. Think of this as a bowl in that is kept in your room. On one side you have M, on the other side you have C, and on the y-axis you have, let's say, MSE. This is a value of M, this is a value of C, and this is MSE, and this whole thing is more or less like a three-dimensional parabola, which is like a bowl. Think of it like a bowl, right? So what we are trying to identify is we are trying to find a particular value of M and the corresponding value of C, and the corresponding value of C where your MSE is minimum. There is one specific point where your M and your C give you the lowest MSE, some specific value in this whole hemisphere. We are going to try and find that. But to find that, what we are going to do is we're going to employ a very simple concept, a concept that we've learned in our, that all of us have sort of learned in our, again, 10th standard only. So the point is to solve for corresponding values of M and C, what we're going to do is we're going to apply a very, very simple concept of maxima and minima, right? So if we remember long ago, once upon a time, we all learned about it, called as something called as maxima and minima. Maxima and minima simply is to find the maximum value or the minimum value of any particular equation. What we will simply do is we simply will differentiate that equation and we'll equate it to 0. So you have MSE. Let me try and simplify this for you. Let's start with a very, very simple equation. Let's say you have a simple equation like y is equal to, So let's say you have a very, very simple equation, which looks like this. Let's say y is equal to 3x square plus 2x, or rather, let's not even go that far. Let's take a simple y is equal to 2x plus 3. This is a straight line equation. I want to find the minimum most value of this particular line. How do I find it? Let's take a 3x square plus 2x plus 1. Let's say I have an equation that looks like this: 3x square plus 2x plus 1. So if I were to find the minimum most value of this particular equation, how do I find it? The best possible way is I differentiate this equation, dou y by dou x, or dy by dx, which will be 6x plus 2, right? This is 6x and this is 2. Differentiation. The ones who don't know, it's okay. Don't worry about it. Don't fret about it too much. Basically, 3x square will simply become, the power will reduce by 1 and this will get multiplied by this value. That's how differentiation works. Similarly, you have 1 here. This gets multiplied by this fellow and it reduces by 1. So x to the power of 0 is what it becomes. So 6x plus 2. So I am at 6x plus 2. I equate it to 0. I get, if I equate this to 0, I get x is equal to minus 2 by 6 or minus 1 by 3. So at x is equal to minus 1 by 3, this equation that you see over here is going to have the minimum most value of y. Okay, to simply identify the minimum most value of that equation, what you simply will have to do is just differentiate the equation and equate it to 0. When you differentiate the equation and equate it to 0, you compute the slope at a given point. Don't worry about it too much, but essentially what you do is you compute the slope. So if you have a parabola like this and you differentiate an equation, you basically identify the slope of that particular thing, right? You find the slope of that particular tangent, right, at different points. So whenever you differentiate, you basically get the equation of the slope. Okay, but then there is only one point where the equation of slope is equal to 0, and that's the minimum most point. So you differentiate and you equate it to 0. So when I differentiate, I get this equation, and when I equate it to 0, that's only this particular point. So that's the beauty about parabola, right? So what we're going to do is we're going to use something very, very simple. We're going to use the same concept and we'll try to solve this particular problem. We'll use the same concept of minima and maxima, and then we'll try to solve this particular problem. Okay, how are we going to do it? Let's go back to this equation that we see here, and in this particular equation, if you observe, I have 119 m square plus 4c square plus 42 mc minus 128 m blah blah blah. So the first thing, I'm going to differentiate this equation, dou msc by dou m. When I say dou m, I'm partial differentiating it with respect to m. That means all my c terms will become 0. So this will become 119 times 2, 200 and, guys, come on, 238 m plus this becomes 0, 42 m, right? So this will become plus 42 c because m becomes 1. This is going to be minus 428, and this are constants, so the whole thing becomes 0. This becomes a 0 and this becomes a 0 because they're constants. That's the first one. Similarly, dou msc by dou c. This will become 8c. And what about this one? Plus 42m, right? Minus 78 is what I'm going to get. So I got two equations. This will be equal to 0 and this will be equal to 0. Two equations, two unknowns. Can I solve this? Two equations and two unknowns. Okay, I get one yes. I'm assuming everybody simultaneous equations. Perfect, exactly. So you simply solve simultaneous equations from here. 42 MC should be 0 no, right? So when I'm differentiating with respect, when I'm differentiating with respect to M, C becomes a constant. So I get 42C. No, there is 42 MC. M is still there. Yeah, I still have the value of M. So that will never become 0. It will only become 42C. M will become so think of it this way. So 42 MC, when I'm differentiating with respect to C, this whole thing is now a constant except for C. So I'll just have 42M. And similarly, when I'm differentiating with respect to C, when I'm differentiating with respect to M, 42C will become constant. I'll only be left with M in that case. Yeah, I hope that made sense. So quickly, can we solve this? Anyone? If C is constant, then we should consider 42C as 42. Yeah, you're right. So no, if C is constant, then if I differentiate 42C with respect to C, then the whole thing will become 0. I mean, if I'm differentiating 42C with respect to M, the whole thing will become 0. If I'm differentiating 42C with respect to C, then it will be 42. So it depends on what I'm differentiating it with. I mean, am I differentiating it with the M or I'm differentiating with C is what matters. Yeah? This thing will determine the whole thing. Yeah. So I'm trying to actually solve the equation at the background. Just give me a second. So you should typically get your X as, sorry, X or rather, oh, good Lord, I made a small mistake. Just a second. I'm almost done. 42, 8, 42M, 78, 428, calculate. So I'm typically getting my value of M. So M is somewhere around 1.057 and C should be, just a second, 4.2. Yeah, perfect. C is 4.2. Yeah, Prerna, you're right. C is 4.2. So these are the values. So net, my final equation looks like this. So what I'm saying is y is equal to 1.05, sorry, mx plus c, right? So 1.057 times m, sorry, times x plus 4.2. That is my final linear regression equation for the data points that I have seen here. It's 1.057 and 4.2. So anybody who's got values around in that particular sense. So for these data points, right, 5, 7, 6, 3, 8, 14, 10, and 7, if you look at all the values, if you actually compute your linear regression equation, the equation will look something like this, 1.057 and 4. Okay, so I do have a few questions here and I'd like to answer them before I move any forward. Okay, why are we differentiating again? Okay, cool. So the differentiation has happened only once, right, Raja? The point is the differentiation that we are performing over here because we have two unknown terms, right? Remember, when we differentiate, the idea behind differentiation is to identify that particular point where the slope becomes 0, right? So what differentiation typically does, right? It enables us to identify that particular point where the slope has become 0. So if you look at this equation, there is one point where the slope has become 0. But how do I know at what point the slope is becoming 0? So first things what I have to do is I have to find the slope of this equation and I have to equate it to 0, right? But to compute the slope of the equation, how do I compute the slope of an equation? The one way to compute the slope of the equation is you differentiate that particular equation, right? When you differentiate an equation, you get the slope of that particular equation at a particular point. So you do a d by dx or d by dy of that particular equation and you equate it to 0. So when you equate it to 0, what you're saying is I am trying to solve for a point where the slope is 0. There's only one point where the slope will be 0. Only at this particular point the slope is 0. At every other point there is a positive or a negative slope. Only at this particular point the slope is 0. That's the whole point in performing differentiation, right? And because I want to identify the slope both to in for M and for C, right? Minimum most point with respect to M and with respect to C. Hence, I'm performing, instead of doing a definite differentiation, I'm doing a partial differentiation. I'm doing a partial differentiation with respect to M and a partial differentiation with respect to C. It's actually very logical if you know the concept of, if you simply understand little of differentiation and derivatives. It's actually very logical to do something like this. But I hope this kind of makes sense to you. Great, wonderful. So is everybody fine with these values of 1.057 and 4.2? I hope everybody's kind of, you were able to solve these two equations and you were able to find the values of 1.057 and 4.2. Yes, very, very nice, Prerna. Good stuff. Now, this is typically how one should solve a linear regression equation. When somebody is given a linear regression problem, this is how one would solve a linear regression. Right? And in a lot of our exams, when we attend, let's say let's say you're doing master's degree or you're doing some kind of a degree, in a lot of our exams, we're essentially asked to solve this whole thing by hand. We're given around data points, 8 to 10 data points, and we're expected to solve for linear regression completely by hand all the way through till the end. Okay? So this is a very common affair as far as regression is concerned, and this is one of the most popular ways of solving linear regression. This kind of a regression technique is called as ordinary least squares. Right? Let me just ordinary least squares. Right? Why least squares? Because we are trying to see least sum of squares or the lowest possible value of sum of squares. Sum of squares is nothing but your MSE. Instead of MSE, mean, basically that's also a mean. So instead of a mean, if you replace it with sum, it becomes sum of squared error. So we're trying to find a mean or no mean, doesn't matter. Nobody cares. So logically, what I could have done is, if you observe, I said MSE, but I did not divide this whole thing by did not divide this the whole thing by total number of observations. I simply summed them. So though I call it mean square error, I actually solved it as sum of square error, because it does not matter, right? Because this is just a constant value. Nobody cares. Even if imagine I divided this whole thing by a constant value, it wouldn't have mattered. So this whole technique is called as ordinary least squares. As simple as that. Now let's try and validate with Excel. Okay. So Arnab, I hope this answers your question. How do you actually find the values of MNC? This is how you find the values of MNC. Does that clarify to you? This is one way of solving MNC. This is not the only way, by the way. There are numerous ways of doing this, but this is one of the most popular way. When the value of MNC are small, of course. But if the values of MNC are very, very large, when I say, I mean, if the number of data points are very large, I'll have too many equations. It becomes very messy. Solving this whole thing for every data point at the same time becomes extremely irritating and very complicated. So things can get a little untidy with large number of data points, but that's okay. At least we know on paper how to solve it. We'll come to how to scale this out later on. Let's come to Excel. Let's take the same data points and let's try to validate this thing here. X and Y. I have X, I have Y, and the values of 5, 8, 7, 14, 5, 8, 7, 14. What are the others? 6, 10, and 3, 7, 6, 10. Wonderful. Okay. So this is it. Insert. That's the simple line equation. Now what I can do is I can simply go ahead and I can try and add a trend line here. So we can go to chart options, add chart element, trend line. Under trend line, you see here, there are different kinds of trend lines that we can add, a linear, exponential, blah, 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 under different kinds of trend lines. We'll come to that in a minute. Let's add a simple linear trend line. And let me just display equation on chart. That's it. Okay. So yeah, your linear regression has been solved here. Your Excel says the value of m is 1.62, whereas we got a slightly different value. We got a 1.07 and 4. Are the points the same? Data points exactly the same? Maybe we made some small error somewhere. 5, 8, 7, 14, 6, 10, 3, 7. Yeah. We probably made a small mistake somewhere. We must have. Somewhere in these calculations, maybe we made a small mistake somewhere. But that doesn't matter. That's okay. So your linear regression equation, according to your Excel, is 1.6286 plus 1.2. That is what we are saying at this particular point. That's it. So we've got a slightly different value of M and C here. I wonder why. Let me just try to understand this. Did we make a mistake somewhere? 7 minus 10 minus 8 minus 14 minus. Can I show the formula you use once again? Which formula are you talking about? This one? 1.6286 plus 1.2. Yeah. Maybe it's a slightly different value. Let me do one small change. Let me make this 10. Yeah, I mean, if you observe this for 3 and 8, this seems to be a good value. I don't know why. I'll just go back to 8. Yeah, I'm not going to worry too much about it. I think what we've solved is not wrong. I know that for a fact because we've solved it by hand. Maybe there's some calculation error somewhere, but I don't think we should worry too much about it. Point is, of course, that when you solve this equal equation, you get there are of course numerous values that are possible as well, but there is one because we've solved it very very deterministically. I don't think there's a I don't think honestly we get different values over here. One thing that we can validate it against is you can compute we can actually check that out as well. One thing that we can validate if these two models are extremely different is 8, 14, 10, 7, 8, 14, 10, 7, 5, 7, 6, 3 is if I can compute the mean squared error on both the models, one that Excel has come up with and one that we've computed, and we can identify which is giving a better prediction. So this is, let's say, the Excel's prediction. So y is equal to mx, which is 1.628. This thing multiplied by plus 1.2. These are Excel's predictions, and prediction when we solved it by hand. This is simply nothing but, what are the values? It's 1.057 plus 4.2. 1.057 multiplied by x plus 4.2. And yeah, look at this. I think both almost have very, very similar predictions. Let's actually try and compute mean squared error. It's going to be average of sorry, squared error is going to be this minus this squared actual value minus predicted value whole square. Similarly, you can do the same thing here as well, but this time it's going to be the actual value is minus the predicted value is this to the power of 2. So if you compute MSE, average of this, and similarly the average of this, the one that we've computed by hand has a slightly higher squared error, mean squared error. I think we made a small mistake somewhere, and that's probably the one that is causing this issue. But that's okay. I think we're not extremely far away from the actual predictions itself. Yeah, it's probably 1 or 2 data points. If you observe, certain data points were actually very, very correct. Like for example, if you see, this has been perfectly predicted. So is the case with 1 or 2 data points. This is the place where I think we went a little haywire, and I don't know. I think where we made a small mistake. We'll have to see where we made that mistake. Then net, I think we've been able to almost find the best possible equation somewhere, except for a small mistake. Arnab, I see a question. Srinath, what function did you use for getting the equation in Excel? What function did I use? Okay, so what I did was simple. So what you can do is forget about this. Once you create this chart, right? Let's say this is axis titles. You can just set your axis titles over here. This is X, and this is your Y. So what you can do is you can just go to on the left top. If you observe, there's something called as add chart element. When you click on the chart, you go to add chart element, and you can go to trend line. If you see, there's something called as trend line, and you can go into trend line and you can select any one of the trend lines that you want. What I would typically suggest is you can just directly select linear, or what you can do is just go to more trend line options, right? So just click on more trend line and go to, I don't know why it's, yeah. So if you observe, there's something called as format trend line, and in here what you can do is you can now select all the things that you want over here. So for example, you don't want to set intercept, you want to display the equation on the chart, and you also want the r squared value to sort of come up. So, and I'll talk about what r squared is in a minute. This will take care of giving you the linear regression equation at this particular point. Now, the point is, I'll talk about what r squared is in a minute. Now, what you can also do is that in this particular example, we only had one single predictor. When I say one single predictor, you just had one value of x at this particular point. But at times you might also want, let's say you might want to perform linear regression with more than one single variable. What do? Right? You would want to perform this linear regression equation with more than one data point at times. So in such cases, we might have to perform something more than a simple linear regression. So currently, this is linear regression, but a simpler version of this equation called a simple linear regression. But then when you have more than one variable, more than one predictor variables, or more than one independent variables. In this case, there's only one independent variable, which is x. But at times you might have more than one independent variables. You might have x1, x2, x3, and so on and so forth. So in such cases, we will perform something called as multiple linear regression. So a multiple linear regression process remains the same. Of course, the process will remain the same. Then the only thing is that instead of fitting an equation that looks like this, we could typically generalize your linear regression equation into something like this. So if it is a single variable, predicted value is equal to beta naught plus beta 1 times x. So in our case earlier, beta naught was simply nothing but this was your c and this was your m, logically speaking. That is exactly what we had. But the reason why we move away from the terms m and c is because, if you were to generalize this for more than one predictor variables, then m and c values may not be good enough. So you say y is equal to beta naught plus beta 1 times x. This is a simple linear regression. But if you have more than one predictor variables, that means I'm trying to predict, let's say, the yield as a function of rainfall. Let's say I'm trying to predict based on the amount of fertilizer used, right? Amount of money that the farmer has, and I want to also predict it against the quality of soil, right? And blah blah blah, 100 other things, right? But this time I am not simply doing yield with rainfall, but instead I'm doing yield as a function of a lot of other variables, because now I'm thinking that, look, yield is not good enough. I might not be able to simply predict the yield based on one single predictor variable. I might need more than one. So in that case, what we do is we move away from a simple linear regression. We do something called as multiple linear regression. But in multiple linear regression, your equation would look like this. Your predicted value is going to be beta naught plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3 plus and so on, beta n xn, where x1, x2, x3, and so on are nothing but your predictor variables. And beta naught, beta 1, beta 2, and so on. These terms are referred to as just like m was your slope, these terms are typically called as coefficients. We call these as coefficients, and this is still your intercept. Okay, so good point. So now I'll explain. In the case of a simple linear regression, what we are doing is we are simply fitting a straight line, right? So if you think of a simple linear regression, you have all your data points, and then you're simply fitting a straight line. But in multiple, and hence the equation is y is equal to beta naught plus beta 1 times x, a simple one-dimensional equation. This is y and this is x. But in multiple linear regression, things are a little different. So you have x1, x2, and y. And what you're going to have is you may have a lot of data points, right? Hence, what we now do, instead of fitting a simple straight line, we fit a plane. Think of that plane. If you can just think of this. Yeah, think of that plane that we're talking about currently. So imagine in your room you have a small sheet of paper that's kind of lying from one corner to another. So this equation that you see here, this, instead of a single straight line, this becomes a plane. So hence this will have the equation beta naught plus beta 1 times x1 plus beta 2 times x2. That is what this will be, right? Then what about if I have 3? Right? If I have more than 3, currently I just have 2. 1 is a straight line, 2 is a plane. But what if I have more than 2? Then we call it as this is a line, this is a plane. But what if I have more than these? So we call that as a hyperplane. So y is equal to beta naught plus beta 1 x1. This is beta, guys. This is not spare my plus and so on. We call this as a hyperplane. And how does it look like? It's hard to envision a hyperplane, but imagine, take a piece of paper in both your hands, right? No, it's not like a dice. Take a piece of paper in both your hands, right? Take a paper, and let's say you're holding both the edges, and let's say you twist your paper, right? Imagine somebody is holding this paper from this corner, right? And somebody is holding this paper from this corner. You rotate this in one direction, you rotate this in the other direction. Imagine you twist this paper a little. So what will happen? So this paper will now start to have some contours on it. This paper will start to have some kind of ups and downs. You think of that. In certain places it will be up, in another place it will be down, things like that. So the point is, with a single predictor variable, you have a very simple equation. With two predictor variables, you have a slightly complex model. With many predictor variables, this surface that you see over here will not be as straight as this. It will start to become more and more complex. Mathematically, this space will become more and more complex. Think of twisting that paper more and more. The more and more you twist the paper, the more and more complicated the surface will become. The point is that linear regression with one or two variables is actually very simple, but with more variables, it actually could yield in a very complex could yield in a very complex surface. And because when you have many variables and you have many data points, at times what happens is solving problems like we just did, right? This whole thing that we just kind of did a while ago becomes a little non-trivial. Yeah, solving it in this particular fashion becomes very difficult because there are too many variables. Then you'll have to perform too many partial derivatives. Too many partial derivatives means very complex solutions. Hence the whole equation becomes very difficult for us to solve. Okay, so that more or less brings me to the end, except for one last point which we will anyways be discussing later on, but I think it's worth talking about it. This concept of r squared. R squared, if you see, observe over here, there's something called as R squared. So when you build a linear regression model, there are multiple ways of evaluating a linear regression model. One of the most popular ways of evaluating the linear regression model is using this particular term called as R squared. R squared is also referred to as coefficient of determination. A popular name for R squared is, so your R squared, a popular term for R squared, sorry, or another name for R squared is coefficient of determination, right? But basically what we are doing over here under R squared is R squared x talks about the proportion of target variable explained, the proportion of variance in the target variable or your independent variable, or your dependent variable, I'm sorry, explained by the model, right? So what we simply mean by this is, when you see your R squared is, when you see your R squared is 0.8, what we are simply saying is that 80% of the variability in your target variable has been explained by this particular model. So the model that you see currently over here explains 80% of the variability in my target variable. My target variable is varying. So for example, over here, there's some variance, there is still some variance over here, there's some variance over here. There is still some variability in my target variable, which is currently not explained. My model had explained all the variability in my target variable, then my R squared would be 0. My R squared would be 100%, or rather 1, a value of 1. So intuitively, your R squared ranges between 0 and 1, where 1 means you have a perfect model, you have a perfect fit with almost an error of 0. Yeah? So it's highly unlikely that you'll get something like this. In reality, if somebody comes up and tells you that they have an R squared of 90%, then I'm very sure they're doing something wrong, because it's unlikely in a modern day, in a real time scenario, you'll get something like that. Right? We'll be hovering somewhere around the 70s and 60s and so on. So because it's impossible to get a model that kind of, or impossible is an incorrect word. Improbable to get a model that gives you an R squared of zero point 0.9. With the current data set, we can achieve, because this is a simple model. I'll show you how you can achieve it. Linear regression, probably it only gives you 80%. If you actually go to polynomial regression, look at that. Polynomial second degree equation. Look at this. Instead of fitting a linear regression equation is 1.6286x plus 1.2. The same thing if you were to solve it using polynomial regression with a second degree polynomial. Look at it. So the equation, if it were to be y is equal to 0.6591 x square minus whatever, blah, 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 your model would have got an R squared of 0.99. And you can try with more complex models as well. Look at this. Third degree polynomial will almost give you a 100% R squared. Just learn that R squared is basically a term that talks about how much of your target variable has been explained by the model. The current model, if it were a polynomial regression, not a linear regression, but instead of polynomial regression, it would have given you an R squared almost close to 1. We are only doing linear regression. Hence your R squared is 0.8 at this particular point. Okay, everyone? Yeah, that's that. That brings us to closure on your statistics with Excel and your basic statistics and statistics with Excel. Just as a quick refresher, what we've covered until this particular point is we've learned simple statistics of how to descriptive statistics like your mean, median, mode, standard deviation, variance, and so on. And then we moved on from there into inferential statistics, where we learned quite a bit about normal distribution. We did some problems with z-scores, and then we moved on and we learned about hypothesis testing, and we learned about three important tests like your t-test, chi-square test, and ANOVA. And in all these three tests, especially in your t-test, we learned about p-value. I mean, in all these tests, we've realized that whenever we perform a test, there is a p-value associated with it, and the corresponding p-value will give you the probability of committing an error if you reject a null hypothesis and things like that. So we understood all of that quite well, to be honest. And then we moved on. And then we wanted to talk about the next thing in statistics, which is statistical modeling. One of the most popular statistical modeling techniques is your linear regression. So under linear regression, what we have explored is we've explored how to perform a linear regression. In today's session, we've explored how to actually solve a linear regression by hand, and we've also understood how to implement the same using Excel. Additionally, we've also looked at how to implement your t-test, chi-square, and ANOVA in your Excel as well. So that is where we are at this particular point. Any questions, any clarifications? Let's take a quick example and we'll try to understand this thing better. So let's say this is X and this is Y. Let's say there are two classrooms, two students, or two sets of students, class A and class B, and both of them have written two different exams conducted by two different teachers, and they've got two different sets of marks. Or another way of evaluating on another typical problem could be, imagine you're currently performing, let's say you're in a production plant, and what you've realized is that currently you've taken a small sample of data points, a small sample of a particular batch. Let's say you're manufacturing a particular liquid or a drug, let's say, or it could be a food product. Take for example a food product, like let's say there's chips that you're manufacturing, or any manufacturing unit, any food manufacturing or any drug manufacturing unit. A typical quality control team, what they would do is they draw samples, right? They would draw typical, let's say they've drawn two different samples from one from a batch that they know is very good, and the other is a batch that they would want to test against. So there is batch A and there's batch B. Batch A is basically the batch for whom they know that that's a very good batch, and batch B is the currently getting manufactured batch. So now what they want to do is they want to evaluate if the current batch and the batch that they know, if the two batches have significantly different means in, let's say, the amount of sodium levels, right? Because chips have a lot of sodium in them. Or let's say beer manufacturing, where there's a ton of sodium that's being added into beer. So you'd want to identify if there's a significant difference in the beer or not, in the sodium levels in the beer or not. So what you do is you go ahead and you capture it. I don't know the metric for that, but let's say let's just identify that there are certain values. So let's say this is batch 1. Similarly, batch 2 is you get some other values. Why would I get 21? Let's say there are batches, batch A and batch B. This is not so two separate batches at this particular point. I'd want to identify if the means are significantly different or not at this particular point. So when I say if the means are significantly different or not, what is my null hypothesis? So Raja, here is where we're trying to identify your null hypothesis and alternate hypothesis. I want to identify if these two batches are significantly different or not, right? To prove that my batches are significantly different. So first things first, what is my claim? My claim is that these batches are significantly different. See, remember, when you perform hypothesis testing, when would you do hypothesis testing? You would do a hypothesis testing when you know that there's something wrong, or when you know that there's something different than the normal behavior. Or you have a feeling that it looks like this is different from the normal behavior. Right? You have a feeling that the current behavior is different from the regular behavior. So what that means is that when there are two different batches of a drug being manufactured or food being manufactured, whatever kind of food, somebody sensed that there could be something wrong, or somebody is assuming that there is something wrong, and they're trying to prove that these are wrong or these are different from each other, right? So then in that case, what is the null hypothesis in general? The null hypothesis is that there's nothing wrong, right? Null hypothesis says no difference. Null hypothesis is you're nullifying the claims. The claim has been nullified, so no difference. And the alternate hypothesis, there is a difference in the mean. There is a significant difference rather in the sodium levels or whatever levels, I don't know what they are, in both the batches. Okay, so now this is my setup, and I'd like to go ahead and perform a simple hypothesis test. So how do you perform a hypothesis test? So let's just go here and go to data, and sorry, just a second. Why don't I see the option here? Just give me a second. Why is it that I don't see the option here to perform a t-test? Sorry, home, data. There must have been a data analysis option here. This is doing with Excel. I don't need to place it in a table actually. Oh, where did this pull this up from? There's a function for t-test straight away. Just give me a second. I think there is an add-in already on my Excel. Something that I've been using for a while. Oh yeah, you're right. So this is a new machine that I'm using since my previous thing. Yeah. Analysis tool pack. So for the ones who've okay, this is a good thing for you guys as well. If you do not already have it, what you could do is you could just go to analysis tool pack under the add-ins section and just hit OK. That should basically install your data analysis. Basically, add your data analysis. Just give me a second. Analysis tool pack, and I had solver. Solver is not needed, but that's okay. Analysis tool pack. Here we go. So that's the only thing that you guys will have to do. If it's already not on your machine, in most machines it will be available. So just go to options, and under options you go to add-ins and just go and select the add-ins that you would want. So analysis tool pack is the one that we would require. If you're doing any kind of VBA scripting, which in this case we are not, we don't need that. Solver is actually quite useful as well. So for example, Solver is a tool that is helpful in performing simplex optimizations and things like that. If you want, you can use it. Ideally, we're not going to need it, but then at least we will require the data analysis tab, so to say. If you go to data analysis, under the data analysis, you have test examples over here. What kind of a test is this? Let's say batch 1 and batch 2. What kind of a test are we talking about over here? Is it a paid sample t-test, or is it a two sample t-test? What kind of a t-test is this? It's a two sample t-test. Spot on, correct? Yeah, it's a two sample t-test because there is no dependency between these two samples. So let's go ahead and click on data analysis, and here if you see data analysis t-test with unequal variances and equal variances. If you're not sure, just click the one that is equal variances. The primary difference between these two is that if you know for a fact that these two are supposed to have the same mean and the same variance, right? If you want them to have the same mean and the same variance, that means both of them have to be more or less the same. In such case, we typically we just don't compare the mean, we also compare the mean with the variances. In the case of that, just go ahead and select a two sample t-test with equal variances. If you're not unsure, it was most likely equal variances. So just select that. Variable range 1, this is variable range 1, variable range 1, variable range 2, and there are labels. Hypothesized mean difference is 0 because I'm saying that both of them have no difference. So the difference in the mean is 0. And I'm going to select an output range where the output will simply come up. So I'm going to select this output and I'm going to hit OK. Boom, done. That's it. So that's my t-test output, as you see here. Now remember, this is a two sample t-test, but is it a two-tailed t-test or a single-tailed t-test, one-tailed t-test? Two sample t-test with, am I interested in, am I directionally dependent or independent in this particular case? I mean, am I looking at should the mean be greater than 0 or less than 0, or the batch 2 mean is greater than batch 1? Okay, I'm independent at this particular point. So hence I'm more interested in a two-tailed t-test. I look at on both sides of the both sides of the mean. I'll be performing a two-tailed t-test, and the corresponding p-value is 2.2. The corresponding p-value is 0.88. Basically saying that these two have a significantly different mean, right? This has a mean of, this has a mean of 15.33 and this has a mean of 15.83. Though the number of data points are quite small, with the current data set, what we are saying is that with equal variances, what we're currently saying is that these two have a significantly different mean. It's probably not simply because of the mean, probably because of the variance that we see that kind of an issue at this particular point. Let's say if I were to, if we just forget about this whole thing, and if I were to, let's say, change this to 21, I go to data analysis and perform the same thing. But this time, if you observe, I get a slightly lower p-value because again, the variance is significantly different from each other. I see that the p-value is still very, very high, saying that these two samples, though they look alike, they probably have a similar mean. But then because of the fact that the variance is very, very different, saying that the p-value is very, very large. Again, remember, this is because we are assuming that there has to be equal variance. Imagine if you were to do the same thing with unequal variance. Yeah, let's go here for this time, unequal variances. And if you were to do the same thing, first one, second one, labels 0, output. Oops, sorry, I have to select output. This is my output. Yeah, even with unequal variances in this particular case, the p-value is actually quite high, simply because I think the difference in the means is quite significant in this particular case. Hence, it says that with the total number of observations that we see here, I also the fact that the number of observations are quite small, it still says that the p-value is actually quite quite high. I would have rejected my null hypothesis if the p-value is less than 0.05. So if somebody is asking that question, p-value is greater than 0.05. Therefore, you don't reject HA, you fail to reject your null hypothesis, right? So you by default are with null hypothesis, right? When you say reject alternate hypothesis, that is typically not the right terminology. You have failed to reject your null hypothesis. Rejecting null hypothesis is your aim here. So you either succeed in rejecting the null hypothesis or you fail to reject your null hypothesis. So currently we are failing to reject the null hypothesis. That's the right terminology. I mean, there's nothing wrong with what you're saying. Exactly. Yeah, you failed to reject null hypothesis in this case. Correct. Yeah. So I hope you're comfortable with this. Yeah, with this example. This is how you typically perform a t-test. Similarly, we've also done chi-square test and ANOVA in our previous session as well. Yeah. So it's the same thing, right? You just go here, select chi-square test, select ANOVA, and then or chi-square test. The point is, ANOVA, we did ANOVA straight away. ANOVA single factor ANOVA is what we already did. Same example, similar example. You could also do the same thing with ANOVA as well. Imagine you had the third batch and you were to compare x1, x2, x3, or the three batches. Then you could simply identify what is the best approach over here, or you could identify if the p-value is less than 0.5 or not, 0.05 or not. Same thing ANOVA as well. Okay. So I think somebody asked me a point.
What I wanted to ask was, when you say this is my claim, it could be, can H0 be not my claim as well? And can that be rejected, or I mean, how does that HA and H0 work? So suppose by accident, if instead of having a claim as which one has got a better quality, or I'm assuming that the amount of alcohol in this particular sample is more than sample B, whatever, and that is my claim. A has got more alcohol than B, let's say, and that's my claim. But my counterclaim could be H0 could be HB has got more alcohol than A. So I mean, how do I does it make a difference at all? That's my question. That would be
it
my
does.
question.
So it does make a big difference. So first things first, I think I think we need to understand the premise or the situation where a hypothesis testing is performed, right? I think the scenarios where hypothesis testing is generally performed is for example, wherever you have, there is a specific process in place, things are happening in a certain order, and now you've started to realize that there is a slight deviation. You did a small test and you've realized that there is some kind of a deviation in the numbers that you're seeing. Do you see a slight difference in the mean, or you see that the variance is slightly higher? You now have a small doubt that, oh, looks like the average age of Indians is not what we had been assuming all these days until this particular point. Yeah, there has been some previous research which was published taking a survey of 1,000 people, and somebody published this number and said that the average age of Indians is 29. Now, when you are doing your own survey, you realize that the average age of Indians is actually not 29. It's actually gone up to 32. So now you have a doubt that there is a difference. There seems to be a difference. Hence, you go ahead and now you're claiming that the average age has gone up. Hence, your null hypothesis is that there is no difference. Why? Because your claim is that there is a difference. Ideally, state of equilibrium, nothing has changed. So that will be your null hypothesis always. If things did not change, if there was no external impact, what would have happened? That would be a null hypothesis. If there was no influence of any external thing, that would typically be a null hypothesis. So a state of no change, a state of no difference is typically what is going to be your null hypothesis. Your alternate hypothesis, on the other hand, is some impact caused by an externally influenced factor. Now that can be anything. I don't care what the factor is. We're not bothered about what the factor is. Empirically, we are trying to identify that, okay, has there been a difference, or there is no difference? That's all that we're trying to identify over here. So your null hypothesis, the reason why we call it as null hypothesis is because it nullifies all claims. And the claim in this particular case is that there is a difference. Why are you making a claim? Because there is a doubt. If there is no doubt, there is no claim. What is the doubt that you have in your mind? The doubt is that, okay, there is something that has deviated from normalcy, right? So if there is no doubt, there is no claim. And if there's no claim, your null hypothesis and there's no concept of an alternate hypothesis over here. Your null hypothesis simply stands. Does that clarify?
Good. Yep, it does. Thank you. Brilliant.
Cool. That's all that I had from me. Any other questions? Data science researchers build new algorithms. Yes, you're right. They actually build new algorithms. They are the ones who are in the forefront of coming up with newer ways of solving complex problems. So they are the ones who, let's say, for example, you have a new way of, let's say, mixing text and let's say images. and coming up with a completely different way of representing data. It's the research field that where all of this happens. It's the data science researchers at Microsoft, at let's say Google and Amazons of the world. They are the ones who are in the front. IBM, yeah, they are the ones ahead in the market. They're the ones building those very, very complex features. But that's more of an engineering. It is. I mean, see. So whenever you talk about a particular problem, right? There are three phases of how a product typically gets built. One is the actual research, the core research of how a problem needs to be solved. So I'll give you a simple question, right? So you have to perform language translation, right? So I give you a piece of English text. You need to convert it into Spanish. The first phase is figuring out the underlying algorithms or underlying math of how you solve the problem. That's the most important piece. Next is scaling this up, right? Actually applying this at a large scale level. The third is once you've cracked how to scale it, then it's about applying this to larger applications, different kinds of applications. So performing language translation in text, performing language translation on top of OCR read documents, performing language translation from languages to, let's say, code. I have SQL and I want to convert ANSI SQL to, let's say, Oracle SQL, or Oracle SQL to, let's say, Teradata SQL. That's basically different applications of the same problem. But cracking the actual problem of converting, of representing text in some numerical format and then trying to solve that and trying to perform translation on top of it, or building architectures where something like this can happen, is a research problem. Once that's done, then you scale this up. So then it becomes an engineering problem. You scale this up, you apply this on large volumes of data, then you operationalize it. That's an engineering problem. And then it's the consulting teams who take this solution, pre-built solution, and apply it on different fields and try and solve the problems, because you have a semi-baked solution. So you take that semi-baked solution and do that final tinkering on different. They basically solve the last mile, so to say. So yeah, I mean that's generally how product development happens. Let's do a simple linear regression equation implementation in Excel, and then we'll see how it actually works. So this is my age and income. Let's say I'd like to predict the income based on the age of a particular person, right? So I'd like to predict income. So income becomes my Y. This is my Y, and this is my X. And so I'm looking at an equation that basically looks like this, which says that income is equal to some value times age plus some other value, something in that form. I'm looking at an equation that looks like that. Okay. So let's actually try and perform a simple linear regression here. And it's actually very easy to do it. Let's go to home and go to insert. Let's insert a chart. This is a simple chart that you see here. Yeah, I don't know why we don't have. I don't know why this doesn't have x-axis elements and y-axis, but that's okay. Let's actually quickly do it. Yeah. Access options, yes. So we can quickly labels. Oh, got it. Thank you for that. Yeah, so you could quickly do this. This is your income, which is your Y, and this is your X, which is nothing but your age, which is your X. Perfect. And then you will also have, and then you can get this. So this is income versus age. I'm just doing some simple embellishments over here, doesn't matter. But the point is, this is how it looks like. Now the next part is that given that your data looks like this, what you could simply do is you could add a simple chart element. You can click on a chart element and you could go to trend lines and then just go to linear. Right, just go to linear trend line, just click on the line, and currently, if you see here, display equation on the chart, and that's my equation. That's it. That's a linear regression that we've just performed. So that's your linear regression equation as of now. So your linear regression basically says that your income is equal to 0.5603 times your x, which is simply nothing but your income, which is nothing but your age, plus 55.647. In this particular case, if you observe, this particular value is very, very similar to that of your correlation. Because this is simple linear regression, your point is very, very true. But then in multiple linear regression, this will not continue to be your correlation. It will be something beyond just that. But that being said, as you see over here, this is your equation as of now. So if I would like to compute, let's say for let's say this is my test set or a new data for, let's say, ages. Okay, let's do for 25 and 25 and 50. Yeah, so not for 25, sorry. Let's do it for new data points. Let's say 56 and let's say 75, and let's say I have one more age which is 15, or let's do 23. I'd want to, for these data points of age, I'd want to compute the income predicted. This is going to be 0.5603 multiplied by your age plus 55.647. That's it. Those are my predictions. So what we're saying is that, because in this particular case, what we're saying is that 56, 75, and 23 were originally not in my data, but then these are predicted values of my current age as of now, of the age values that you see over here. So you could use, the whole problem is to go ahead and identify what these values are typically going to be. Yeah, your intercept values are actually going to be. Okay. So that's it. That's how you typically perform your linear regression. What about the points when age is 25 and 50? So what has happened here? What has happened when the age is 25? Yes, they are not touching the line. In fact, as a matter of fact, this line is not touching any of the data points. If you observe this closely, this line is actually not touching any of the data points. What does that tell you? Remember that this is just one single data point which has an erratic behavior. Rest all the other data points are over there. So would you expect this line to actually get skewed towards this one single data point, or do you expect the line to stick towards the majority? Here my question before we jump into any conclusion. There is a big difference between, okay, mathematics has two kinds of concepts. One is called as curve fitting and the other is called as regression, right? Curve fitting is a process of trying to find a curve that connects all the data points. Right? Curve fitting is a process which tries to find an equation which tries to find a complex mathematical equation which connects all the data points. But then the problem with curve fitting is that, when I say curve fitting, what I essentially mean by that is that you would basically have something that looks like this. So you're going to have something that looks like that, which connects all those data points. But then the problem is, with an equation like this equation is a very, very complex equation, and identifying this equation is non-trivial, first things first. But then my purpose behind linear regression is not to find an equation that connects all the data points. No, that's not the whole point. Predictive analytics is not trying to give you an accurate representation of what has happened in the past. No, a predictive analytics is trying to identify a majority trend of what has happened in the past and try and generalize that pattern for the future. So we are doing pattern extraction. We are not trying to perform curve fitting. We are not trying to find a line that connects all the data points. Nope, that is not the purpose. Because And remember, this is all observed data, and observed data can be extremely erratic. In a year like COVID, you will definitely see these random data points. You know, either you having very low sales or having extremely high operating costs and things like that. But I do not want to form an equation that connects all the data points. I want to learn patterns learn the majority pattern from historical data and try and generalize that for the future. Try and use that pattern and predict what is likely to happen in the future. Right? I don't want an exact line, but I want a pattern that is sort of that captures the majority trend. That's the primary purpose, Dave. Does that make sense? Hence, though this line that you see over here is probably not the best of the best quality, or this line that you see currently does not have the best behavior, I am still happy with this. I'm still happy with this because it still kind of captures the majority trend. And the majority trend is that everything is increasing. So the line captures that increasing trend. Well, will it give me the best possible prediction to the fifth decimal? No, that is, it is not meant to do it, and it is unfair for me to expect something like that from here. So it will give me some form of guidance, but I will not probably expect it to give me 100% accurate prediction. I would be a fool to expect something like that from linear regression, right? So we're doing, remember, data science is all about pattern extraction. So if there's a pattern, we'll try to extract it. If there are one or two data points which kind of deceive or which kind of do not follow the pattern, we'll try to ignore them to the extent possible because they don't fit into the pattern. If by removing those one or two data points, if I'm able to capture a pattern, I will go ahead and do that. I will forget about the fact that that data point exists. So most of the concepts that you will learn will always be inclined in that direction. You will always see that your patterns will always try to you will always try to ignore these incorrect data points and still try to go ahead and create a pattern. So that's exactly what linear regression is still doing over here. But remember one thing, if I remove my line is still taking this fellow into consideration, because if I remove this one single data point, if I remove this one single data point, which is that 150, right? Yeah, if I remove this one single data point, look what happens then. If I just remove that one single data point, my equation becomes much more accurate. But because of the presence of that one single data point, my equation hasn't been that accurate. So I tried, it tried to kind of bring it together, but the impact of that one or two data points is much more, is quite less, so to say. Yeah. Dave, you're correct. It's predictive analytics. It's approximations rather than behavioral analysis. I don't care about what that single data point is. I'm rather more interested in the overall pattern. I want a pattern that I can generalize. So what am I able to generalize now? I'm able to say that, okay, in general, I could expect, my predictive analysis tells me that given a certain value of age, or let's say for an age of 56, I could expect the prediction to be somewhere around 87 or so. Okay, great. And we might be completely incorrect. It's okay. I mean, if you're incorrect, we're incorrect. There's nothing wrong about it. But then we'll evaluate how good or how close or how far away we are, and then you'll also see that there are certain ways and means to ignore those data points and identify only the valid ones. And we'll also learn about ways and means to eliminate data points which are incorrectly behaving, and so on. So there are different techniques that are available. Okay, cool, wonderful. So that's how you simply perform a simple linear regression in your in Excel. Okay, and that's a nice segue into learning Excel. So we're going to learn how to perform a couple of other tests in Excel as well. Why Excel? Probably because it's a part of your course. I think the primary reason behind why Excel has been included as part of the course is that Excel actually provides you a lot of cool, quick ways of performing some analysis. Like for example, doing this linear regression, what you would have probably had to write a few lines of code in Excel, in let's say in Python or in R. But Excel has some cool, quick, dirty analysis, quick ways of doing some analyses, right? So it's like that tool which has been there for a lot of time but is super underrated, and but has a lot of value also from a statistics standpoint. So Excel would, if you ask me personally, there's a lot of tools that are available, like let's say your R, Python, Excel, NIME, Veka, SPSS, SAS, SPSS, Alteryx. There are millions of tools that are available today, and I'm sure there are 100 others which are currently in development, and all of them say that this is better than the previous one. So there are numerous tools that are there, but then we try to work with the most simplest ones that are available outside and the most comprehensive ones that are available outside. Currently, the most comprehensive tools that are there are Python and R, for sure. But then for somebody who has been in this field and who wants to get into this field but not write code, Excel is a good tool. All right, it's a quick drag and drop tool. It's easy to work with. You can select certain data points and get done with things. That's the first thing. And all of us know Excel, and given the fact that we've learned some kind of statistics until this particular point, we will use Excel to learn those quick statistical tricks in Excel first, and then we'll try and learn them in R and Python. And Excel is not built to solve complex problems. Excel is built to solve simple reporting problems, simple, easy, quick, dirty kind of analysis. But then anything over and beyond what or anything over and beyond, let's say, simple statistics and basic statistics and some simple inferential statistics, Excel is not meant to do things like those. As a matter of fact, Excel has a limitation of 1 million rows, right? Anything beyond 1 million rows, Excel actually doesn't work with it. Or I think they've kind of come up with a 10 million row limitation. So the point is that Excel is not meant to solve those kind of problems, but Excel is a good start point for somebody who's onboarding this journey. So you want to do some quick, dirty analysis, Excel is a good tool. I don't personally work on Excel as much. Long gone are those days where I work on Excel. But then what I'm going to concentrate on is I'm not going to teach you all how to create charts. I'm not going to teach you all how to I'm not going to teach you all how to add two numbers in Excel, because all of us some form or shape have learned Excel. So this course or this next few hours, I'd like to make it as useful as possible for you guys. So what I'm gonna do is I'm gonna try and teach you all um, how to do these quick statistical analyses that we've learned over the last few days in Excel. Right. So for example, doing some basic statistics, computing correlation covariance, we've already done that. Doing linear regression, we've already seen that. Or performing, let's say, t-test chi-square ANOVA. Those are the things that we'll try and learn in the next few minutes. Those are things that I like to concentrate on rather than actually learning how to save a file and how to open a file and things like that. I hope we don't need those. Yeah. So okay, cool. So that brings me to a couple of quick points. First things first, as Excel as a tool has got a lot of cool functionality, a lot of functionality that probably we don't even know exists in the first place. A few things, of course, that we're going to learn over here are, when you have certain amount of data that is available, how can you apply simple, quick statistical analysis? How can you perform quick statistical analysis using Excel? Like for example, first things first, let's say I have a bunch of data. I'd like to perform a quick analysis on quick some kind of a t-test or some kind of ANOVA that I like to perform. What I could do is, let's quickly try and do that. Right. So let's say this is the data that I have, and let's say these are and let's say this is the height of the crop from field A, and this is field B, and I'd like to perform a quick and these are basically two samples, sample A and sample B, two fields, and I'd like to identify if the mean of these samples, if they're significantly different or not. Or rather, my null hypothesis is that the mean is the same. The alternate hypothesis is that the mean is not the same, right? So I'm typically performing a two sample, two-tailed t-test. That's essentially what we're trying to do over here. So the way to do that is, I mean, there are numerous ways of doing this. There is a t-test function that is readily available. I could directly apply the t-test function. But then if you want to go do it a little more visibly, what you could do is, in general, you would find something called as data analysis as a tool. Just click on data analysis. And under data analysis, you would see that there is something called as a t-test two sample assuming equal variances. So you could do that. You could do a quick two sample t-test, right? So let's quickly select. This is my data set as array 1, variable 2. I'm selecting my variable 2 over here, and then hypothesize the mean difference. So I'm saying that the difference in the mean is 0, right? So hence the difference of the mean is 0, or rather it's basically saying that the means are the same. So the hypothesis is that the means are the difference in the mean is 0. Labels are not there in the data. That's okay. Alpha is 0.05. You can change whatever your alpha value is, and then I can simply select an output range. I can select the output range over here, right? And then I can simply click on OK, and that's it. That's my result that I've got, right? There's a lot of content here. We don't have, and everything is actually quite simple. This is a mean of variable 1, variable 2. Actually, let's do one thing. Let me do this actually. C4, yes. Let me click labels. Okay, cool. My bad. Just give me a second. Data analysis. Okay, let me click this off. I could have selected it from the top, but that's okay. Variable 1, variable 2. This is basically field A and field B, right? So for field A, this is the mean of field A, mean of field B, and variance of field A and variance of field B. And these are both the variances of field A and field B. Observations, 7 observations each. Pooled variance is basically together the variance of all the data points put together. Degrees of freedom is 12. That's fine. And because totally we have close around 14 observations, so 14 minus 1 is basically 12 observations that we have totally. And then you have the corresponding t-statistic. The t-statistic is 0.35. So t-statistic that is compared with 2-sample t-test. We've already learned that. Now, is this a one-tailed t-test or a two-tailed t-test that we've performed? What is the alternate hypothesis? Now, what is an alternate hypothesis? That the means are unequal, right? So I'm not worried about greater than or less than. So currently I'm interested in a two-tailed t-test. Hence the p-value with a two-tailed t-test is 0.72. So the probability that these two are, or the probability that I would commit a mistake if I reject my null hypothesis is 72%. So what happens now? Should I reject the null hypothesis or should I stick with my null hypothesis? H. Huh? You stick with your null hypothesis. You don't reject your null hypothesis. You cannot reject your null hypothesis, because if you reject your null hypothesis, the chance that you would be committing a mistake is 72%. This is the value that you need to be looking at. So there's no way you can reject your null hypothesis. Guys, remember, my alpha is 0.05. This is 0.72. My p-value is way greater than 0.05. So you would not reject your null hypothesis. So you would not reject your null hypothesis. You would go with your null hypothesis, or you fail to reject your null hypothesis in this particular case. Okay. So yeah, correct. So you would go with a null hypothesis, and the null hypothesis says that these two are almost the same. So what we're saying is that there is no significant difference in the means between these two groups. Exactly. Okay. That's it. A simple t-test is performed. Similarly, there one point to understand is that there's no way to actually perform a one sample t-test in Excel. Excel only gives you a 2-sample t-test. Excel doesn't let you perform a 1-sample t-test, or you can also perform a paired t-test, but you cannot perform a 2-sample t-test, a 1-sample t-test. I'm sorry. Okay. Let's say let's say you were to right. Let's say you're computing the or rather before and after, and let's say I'm trying to compute the diabetes levels of people before taking a drug and after taking a drug. At the same person, I'm trying to compute the diabetes levels before taking a drug and after let's say after a course of taking a certain medication of let's say 2 weeks, I'm trying to compute the let's say the diabetes levels. Let's say it's a random blood sugar that I've captured, and I'm trying to compute the blood sugar levels. Somebody who's got a 250, and then and then this is 180, 220, let's say 210, 170. Let's say this is 60. That's sorry, 150, and so on and so forth. Let's say you have one. Let's come up with one more data point, 121, and let's say this particular person has dropped to 90. Okay, so now what we are saying is that there is a set of people. There are data points over here, but this time this is, remember that this is the same person, right? Person 1, person 5. So 5 people who did the test before taking a medication and after taking a medication, and we've captured their blood glucose or random sugar levels in their bodies. Now I'd like to identify if these values, if there is a significant difference before and after taking the medication. Okay, I'd like to identify if the difference is significant or not. So what kind of test am I applying here? Is it exactly, it's a paired sample t-test, correct? Paired samples, because this is a pair. It's the same person, but there's a pair over here. Both these observations belong to the same person over here. Hence, I'll have to perform a paid t-test over here. So to perform a paired t-test, let me just go to data analysis, and then there's a paid 2 samples for means. So the first one is this. Let's say select from here to here. And then the second is from here to here. And then I'm saying that the difference is 0, that there is no difference. My null hypothesis is that there's no difference. And let's say my output range is just here. So that's a quick paid 2 sample t-test for means. This is before and after. The mean before is 190, the mean after is 150. The variance is almost similar. In this particular case, the observations are 5 and 5. The correlation is 0.83, some kind of correlation that has been computed. It's a p, again, a two-tailed test. So your p-value is 0.033 with an alpha of 0.05. What would you do? Would you select your null hypothesis, or your null hypothesis again, of course, is that there is no difference, and the alternate hypothesis is that there is a difference. So what would you say? Do you think the drug actually had an impact? H0 is rejected, correct. So do you think that the drug actually had an impact on the person, on diabetes levels? Yes, it has. Yes, it has an impact, because the differences in the mean are significant. Hence, the drug has a significant impact on the outcome. Absolutely correct. So that's how you quickly perform a t-test, so to say. Similarly, if you were to perform, let's say if you were to do some kind of an ANOVA test, remember yesterday's example. We'll come to chi-square in a while. There's no straightforward way of doing a chi-square, but let's look at ANOVA. So there are 3 classrooms, and these are the marks achieved by the 3 students from these 3 classrooms. And I'd like to identify if the means are significantly different or not between these 3 groups. If there are only 2 groups, I could have directly done a t-sample. I could have simply done a t-test, a 2 sample t-test. But here I have more than 2 groups. I have 3 groups over here currently. So the way I would perform is I would be performing an ANOVA. So go to data analysis and ANOVA single factor, because I just have one factor over here, which is nothing but your classroom. One categorical variable, it's a single factor. So now I would be performing input range. I can select my input range over here. This is my input range, and grouped by columns, because each column is a group. If you remember, if you see this one, each column is a group. And label in the first row. Yes, there's a labels in the first row. Alpha is 0.05. Output range. Let me select my output range over here. That's my output range. So now what am I saying? In this particular group, the null hypothesis is that the means are not significantly different, or rather the variances in these groups and the means are not significantly different. The alternate hypothesis is that these 3 groups actually behave differently. Right? There's actually a significant difference between these 3 groups. Click on OK. You quickly get the summary, single factor ANOVA, right? So group ABC, this is the quick 5-number summary, count, sum, average, variance of your group ABC. And here is where you have the ANOVA. Between groups SS and within group SS, these are the degrees of freedom. This is your mean sum of squares. Basically, this divided by the degrees of freedom and this divided by degrees of freedom mean sum of squares, and the corresponding F statistic and the corresponding p-value. So your p-value is 0.001852. So what do? Do you reject your null hypothesis or accept your alternate, or do you reject your null hypothesis or not? In this case, with an alpha of 0.05, you successfully reject your null hypothesis and you reject your null hypothesis and you go ahead with your alternate hypothesis of the fact that the classrooms or the three streams of students actually are significantly different from each other. That's it. So a few clicks and your ANOVA is done. Similarly, what we will learn in our subsequent sessions, just like how we've learned to do t-test and ANOVA in our current session, we will learn how to, let's say, perform a chi-square test. There is no straightforward way of doing a chi-square test. There is actually. Thank you very much, everyone.